Hello everyone, I'm Huan, and today I'm going to introduce our work on meta-auxiliary learning for future depth prediction in videos. We will start from introducing the prior arts. There has been a line of work on predicting future information in videos, such as future RGB frame and future semantic segmentation. However, future depth prediction has not been studied before. This paper presents the first work on this topic. Since the problem of future depth prediction is rarely explored, before we start introducing our work, let's take a look at the problem definition. Given a few observed frames such as the frames at the time step t-3 to the t, the goal is to predict the depth map of a future frame such as the frame at time step t+1. A naive solution of future depth prediction is to treat it as a purely supervised learning problem. We can learn a mapping using deep learning model between the input frames and the ground truth steps. The limitation of this approach is that the learned model tends to overfit to videos used for training and do not generalize well to unseen videos, especially when there is a large domain gap between the training and the testing videos. In this paper, we use a meta-auxiliary learning approach for future depth prediction. Instead of treating future depth prediction as a purely supervised problem, we add an auxiliary task that is complementary to the primary task of future prediction. These two tasks share the backbone for feature extractions and learn together. The auxiliary task acts as a regularization that helps learn feature representations that are useful for the primary task. To facilitate the effective test time adaptation, we propose a meta-auxiliary learning approach for training the model. There are two phases in the meta-auxiliary learning, that are meta-auxiliary training and testing. We conduct the meta-auxiliary training to let the model learn how to adapt to unseen videos, and using meta-auxiliary testing to adapt to the test videos. The meta-training process involves a nested loop. In the inner loop, we sample a batch of training data. For each instance in the batch, we update the model parameters via the auxiliary task branch to obtain a model adapted to this instance. We then evaluate the adapted model using the loss for the primary branch. In the outer loop, we update the global model in a way that minimizes the primary losses in the batch. During meta-testing, we are given a new video. We use the auxiliary branch to obtain the adapted model for this video, then use the adapted model for predictions in the remaining frames of this test video. The quantitative results demonstrate that our proposed approach outperforms other alternative methods. We also conduct ablation studies. We compare with methods by removing various components of our proposed methods. It shows that the performance of the methods with our full solutions is the best. The additional analysis on the batch size suggests that the larger the batch size, the better the performance. This is a qualitative result. It can be observed that by performing test time adaptation, the depth map is virally better than the compared. Thank you. That's the end of this presentation.